A telescope more than 1 million miles from Earth is quietly changing everything we thought we knew about the universe. The James Webb Space Telescope has captured details that were once hidden in the depths of time. This year alone, its discoveries have already changed the way we think about the birth of stars and the formation of galaxies several times over. The uniqueness of JWST lies not only in the beauty of the images but also in the accuracy of the data. Galaxies that once appeared to us as dim spots now reveal their structure, star formation rates, and even the violent processes that govern their evolution. The telescope's unprecedented resolution allows us to peer into the regions where stars are born, giving us a glimpse of the complex interactions that shape the modern universe. In this video, we've compiled the most remarkable discoveries made by JWST this year, each one putting our previous theories to the test. Each one bringing us closer to answering fundamental questions about the universe and our place in it. Galaxies and their endless interactions often create strikingly beautiful yet scientifically profound visual images. One such example, observed by the James Webb Space Telescope this September, is the collision of two galaxies known as ARP 107. This event bears an unusual resemblance to a smiling face. The collision, occurring about 465.5 million light-years away in the constellation Leo Minor, involves a large spiral galaxy and a smaller elliptical galaxy. The JWST's near-infrared camera and mid-infrared instrument revealed intricate details that stunned astronomers. Most noticeable in this cosmic smile is the nearly transparent bridge of stars that has been pulled from both galaxies and stretched between them like a thin thread. Areas of active star formation, new stars born from turbulent gases displaced by the merger, glow in orange and red hues. This image tells us about the processes that occur during collisions of this magnitude. Events like this can have two seemingly contradictory effects on galaxies. On the one hand, disruption compresses gas clouds, which excites and accelerates star formation, creating clusters of newborn stars in regions where galaxies collide. On the other hand, collisions can disperse and accelerate gas, depriving parts of galaxies of material, which can lead to the starvation of stellar birth in other regions. What's even more interesting is that the large spiral galaxy in this system is classified as a Seyfert galaxy, one of the largest families of active galaxies. Such galaxies have high-energy nuclei dominated by supermassive black holes. In the case of ARP 107, the central region of the spiral galaxy emits energy at a level far beyond what can be explained by ordinary stars. However, unlike the most active galaxies, Seyfert galaxies such as ARP 107 are less bright, making them easier to study in the infrared spectrum, the main band used by JWST. Even the galaxy retained much of its overall structure, except for its distinctive spiral arms, which were almost completely obliterated. This observation demonstrates how even off-center collisions can cause significant changes without destroying the entire system, and contrasts greatly with the more direct, head-on mergers that typically produce chaotic, irregularly shaped galaxies. ARP 107 today continues its slow gravitational absorption, which will continue for hundreds of millions of years, eventually forming one large, irregularly shaped galaxy. Such things are not uncommon in the universe, but the details that JWST provides allow us to observe and analyze these processes like never before. A little earlier, JWST also shed light on details about another interesting galaxy that has given us important clues about the cycles of birth and destruction that shape the cosmos. Located about 15 million light-years away, M83, also known as NGC 5236, stands out among spiral galaxies not only for its characteristic barred structure but also for the active stellar processes taking place within it. The center of M83 is a hotbed of star formation, especially visible in the intense blue regions captured in JWST images. Here, we see a huge cluster of stars closely packed together. Even more exciting are its spiral arms, extending from the core regions known as stellar nurseries. These regions, where new stars are actively being born, are highlighted in bright yellow and orange colors in JWST images. They are rich in gas and dust, particularly polycyclic aromatic hydrocarbons, complex carbon-based molecules that often accompany star formation. JWST's ability to detect these compounds is crucial for studying the chemistry of star-forming regions, allowing us to understand the building blocks of the stellar life cycle. By observing M83 at wavelengths between 5,000 and 28,000 nanometers, JWST can penetrate through the dust that normally hides these stellar nurseries from optical telescopes. These detailed images provide a fundamental tool for understanding the process known as stellar feedback, how young, newly born stars interact with their environment. When forming, stars release energy and eject material in the form of stellar wind and radiation. This feedback can either compress nearby gas, triggering further star formation, or disperse the gas, stopping the birth of new stars in surrounding regions. By carefully studying galaxies like M83, researchers working on programs such as feedback in emerging extragalactic star clusters (FEAST) seek to unravel how such feedback mechanisms operate in different galactic environments. The results obtained on M83, as well as on other galaxies in the FEAST program, will help refine the models that astronomers use to simulate star formation throughout the universe. Presented to us was one of the most active star-forming regions in our galactic neighborhood, located about 161,000 light-years away in the Large Magellanic Cloud. N79 is a prime example of a star factory where new stars are forming at a highly accelerated rate. Unlike its better-known neighbor, the Tarantula Nebula, N79 has remained relatively unexplored until now. The striking starburst pattern emanating from the nebula's core is immediately apparent in the JWST image. This effect is not an intrinsic feature of the nebula but rather a consequence of the way JWST's segmented primary mirror collects light from particularly bright objects. These diffraction peaks emphasize the intense light of a young forming star barely visible in the visible wavelength range but revealed through the power of infrared observation. The orange and red regions surrounding this core are huge clouds of molecular gas, the raw material from which new stars form. In these regions, massive clumps of cold hydrogen gradually condense under the action of gravity, triggering the star formation process. Protostars, still in their native gas envelope, are particularly important for understanding stellar evolution. They represent the initial stage of a star's life, when nuclear fusion has not yet begun in their cores. As mass is gained from the surrounding gas envelopes, they eventually reach a point where the internal pressure and temperature become sufficient for hydrogen to fuse into helium, officially marking the birth of a full-fledged star. Another exciting aspect of the discovery of the N79 nebula is its potential to shed light on the early universe. By studying local processes, astronomers can gain insight into the conditions that prevailed during the most intense period of star formation in the cosmos. Also, this June, Webb gave us another interesting example of star formation by observing the spectacular Serpens Nebula. In this region, located about 1,300 light-years from Earth, a remarkable phenomenon has been observed: protostellar outflows, jets of gas erupting from young stars. Although such outflows have been observed before, the accuracy and clarity left much to be desired. These jets represent one of the earliest stages of a star's development, when the gas collapses under gravity to form a protostar. Some of the material is trapped in jets that fly out of the star's poles at incredible speeds. However, the unique arrangement of these jets in the Serpens Nebula provides new insights into a process that, until now, could only be hypothesized. The jets flowing in the same direction provide strong support for the long-standing theory that stars forming in the same region orbit in the same direction. What makes this discovery even more significant is the permanence of this alignment, which NASA scientists have likened to sleep falling during a storm. This metaphor emphasizes the striking orderliness in the chaotic environment of star birth. The implication is obvious: these aligned flows serve as a kind of historical record of the rotational dynamics in the gas and dust clouds. As stars form, they inherit the angular momentum of the collapsing cloud, which leads to synchronous motion. One of the most striking aspects of this photo is the appearance of an hourglass-shaped shadow cast by one of the young stars. This shadow is a direct result of the jets giving the surrounding gas such a striking shape. JWST's nebula observations are not just limited to star formation, they also provide crucial information about the evolution of the disks and material surrounding these young stars, key ingredients for planet formation. By capturing these jets so early in the development of stars, astronomers can begin to piece together the complex processes that lead to the creation of planetary systems. But Webb's June discoveries don't end there. WSP-39b, a gas giant located 700 light-years from Earth, represents one of the most intriguing planetary environments ever observed. Thanks to the unprecedented sensitivity of the Space Telescope, we now have a clearer picture of the extreme climate of this exoplanet, a world divided between eternal day and endless night. This exoplanet is tidally locked, meaning that one side of it is always facing the star and basking in the sun's rays, while the other is in perpetual darkness. This sharp separation creates a unique atmospheric environment that completely rules out the possibility of life and takes our understanding of planetary climate dynamics to a new level. The JWST near-infrared spectrograph NURSPIC allowed astronomers to measure the temperature differences in these regions with an astonishing level of detail. At first glance, it may seem like a world of absolute scorching heat on one side and icy cold on the other. But the real allure lies in the so-called gray zone between these extremes, where the temperature transitions from the day side to the night side. NURSPIC data shows that the temperature difference between the dawn and twilight regions is an impressive 300 F. On the dawn side, the temperature stays around 150 F and rises to about 1450 F in the evening. JWST also discovered impressive weather patterns on the exoplanet. Winds sweep across the surface at astonishing speeds of thousands of miles per hour, transferring heat from the day side to the night side. This atmospheric circulation is critical to maintaining the balance of temperature on the planet. Interestingly, the dawn side, where night turns to day, tends to be more cloudy. Thick layers of gas form in this colder region. In contrast, the evening side, where day turns to night, appears much clearer, with fewer clouds, perhaps a result of the warmer temperatures displacing condensed gases. These discoveries challenge previous models of exoplanet atmospheres, especially on worlds in tidal capture. Understanding how atmospheric circulation, temperature variations, and cloud formation act on WSP-39b provides insight into how planets with extreme climates can evolve. More importantly, it opens new avenues in the search for potentially habitable planets, as scientists can apply these observations to smaller, rocky exoplanets that may have similar gaps between day and night. By precisely measuring the composition of its atmosphere, JWST has detected trace amounts of molecules such as water vapor, carbon dioxide, and sulfur dioxide, giving us insight into the chemical processes that take place on similar planets. This detailed analysis of the atmosphere is of great importance to the search for life beyond Earth, as it allows astronomers to improve their methods for detecting biosignatures. A month later, in July, Webb pleased scientists with another discovery. This study, published in the monthly notices of the Royal Astronomical Society, concerned brown dwarfs, but this time on a more extensive scale. Brown dwarfs, often referred to as failed stars, occupy an interesting intermediate position between planets and stars. Although they lack the mass to ignite nuclear fusion in their cores, their atmospheres are far from quiet. The James Webb Space Telescope recently allowed us to study in detail the chaotic weather systems of two nearby brown dwarfs, WISE 1049a and WISE 1049b. These observations have given us a rare glimpse into the atmospheric processes of these enigmatic objects and hint at what we can expect from giant exoplanet with similar conditions. The weather here is far from ordinary. Infrared instruments have shown that both objects are engulfed by colossal, turbulent clouds composed of silicate grains, essentially hot sand swirling in the atmosphere. These clouds, fanned by winds moving at tremendous speeds, create a dynamic environment with temperatures ranging from 1610 F to 1880 F. WISE 1049a completes a full revolution every 7 hours, and its brother, WISE 1049b, rotates even faster in just 5 hours. This rapid rotation contributes to the extreme variability observed in their atmospheres. However, the observations do allow us to see how these atmospheres change over time. JWST has taken pictures of the light curves of these brown dwarfs, which show significant variations indicating stormy weather conditions and shifting cloud cover at different altitudes. The light curves obtained with JWST show how clouds evolve at different altitudes, sometimes exposing deeper layers of the atmosphere through gaps in the cloud cover. These variations are associated with different chemical compositions at different depths of the atmosphere. By examining specific wavelengths of light, JWST has found evidence of carbon monoxide, methane, and even silicate grains absorbing into the atmosphere. Each of these chemical markers tells a story about temperature and pressure at different depths, offering a vertical profile of brown dwarf atmospheres. Part could be the remnant of another galaxy caught in the process of merging. If this interpretation is correct, the question mark is more than just an unusual shape, it is a snapshot of cosmic evolution, revealing the dramatic gravitational forces at play as galaxies collide and reshape over millions or even billions of years. Future observations with JWST or other advanced telescopes may provide more insight into the nature of this enigmatic object, potentially confirming whether it is a single distorted galaxy or a pair locked in a cosmic dance. Regardless of its exact nature, this discovery highlights how JWST's powerful infrared vision continues to uncover the unexpected, raising new questions and offering fresh perspectives on the history and evolution of our universe. Light. These jets, powered by supermassive black holes, play a crucial role in galaxy evolution, not only shaping the structure of young galaxies but also regulating star formation by either compressing or dispersing surrounding gas. JWST's observations have allowed astronomers to witness this process in unprecedented detail, confirming that these interactions between black holes, jets, and gas clouds were already shaping galaxies in the earliest epochs of the universe. By studying these early galaxies, scientists can better understand how the first massive cosmic structures emerged from the primordial gas clouds left over from the Big Bang. The discoveries made by JWST this year alone have already challenged some previous theories about galaxy formation, leading to new questions about the complex forces that shaped the early cosmos. As the telescope continues its groundbreaking observations, astronomers anticipate even more surprises, insights that will push the boundaries of our knowledge and bring us closer to answering some of the deepest mysteries of the universe.